Now that we have familiarity with functions, let us analyze them a bit deeper. In particular, when using a function to model a practical situation, it is often useful to consider the rate of change of that function. That is to say, the change in output as you change the input. For instance, when we consider f of t to be the location of an object as a function of time, then the rate of change is the object's velocity. When f of x is the vertical height of a train track as a function of its horizontal distance, then the rate of change is just the slope. In general, we obtain the rate of change of a function over some interval by dividing the change in output value delta y by the change in input value delta x, to get the average change in output value over the interval. Of course, this is only the average change in the function over that interval, and the function may even increase first and then decrease later. We can get a better picture of the situation by considering a smaller interval. If we keep making the interval smaller and smaller, the width of the interval delta x gets closer and closer to 0, and the difference quotient gets closer and closer to the instantaneous rate of change, which we call the derivative at the point x equals a. We will see how to compute this value later on. First, let's consider the graph of a function. Then we see that we are dividing the change in height of the graph over the interval by the width of the interval. Another way to see that is as the slope of the straight line connecting the point on the graph at the start of the interval with the point on the graph at the end of the interval. Again, this is only the average rate of change, and so we may make the interval smaller to obtain a new average rate of change over the smaller interval, again represented by a different straight line. If we keep making the interval smaller and smaller, the straight line will approach the so-called tangent line at the beginning point of the interval. This is the straight line that only touches but does not intersect the graph at that point. Its slope is the instantaneous rate of change of the function at that point. It therefore is the slope of the graph at that point. We may denote this instantaneous rate of change as f prime of a, and this means the tangent line at that point has the equation you see on the slide. Indeed, it passes through the point with x-coordinate a and y-coordinate f of a and has the correct slope. We call this instantaneous rate of change the derivative of the function f at the point a, and denote it either with the prime notation seen before, or the notation df over dx at the point a. Of course, if we vary the starting point of the interval, we can also consider the derivative of a function at any other points in its domain. There are cases where a function does not have a well-defined derivative at a point x equal to a. Namely, when the function has a jump at that point, in which case the instantaneous rate of change is infinite. Or when the function has a sharp kink at that point, in which case there are two different options for the instantaneous rate of change. In these cases, we say the function is not differentiable at the given point, and otherwise we say it is differentiable at the given point. So, assuming that the function is differentiable at each point in its domain, this means we can associate to the function f another function called simply its derivative. This new function is denoted either by f prime or by df over dx. It is defined as the function that associates to each point a in the domain of f the derivative of f at that point a. Before we consider how to compute the derivative of a function, let's also note that since the derivative of f is again a function, it is often possible to take the derivative of this function again to obtain the second derivative, and then again to obtain the third derivative, with the notation as given on the slide. So, how do we obtain the derivative of a function? The first most basic tool is to consider some standard given derivatives, such as the fact that the derivative of the sine function is the cosine function, and the derivative of x to the power 3 is 3x squared, and combine these with computation rules for derivative, such as the chain rule, which states that the derivative of a composition of f of g of x is the composition of the derivative of f with g times the derivative of g. For instance, this shows that the derivative of the function sine of x cubed is 3 times x squared times cosine of x cubed. Following this video, there will be a list of such standard derivatives and computation rules that should allow you to compute a wide range of derivatives already. Please practice this in the exercises following that list. For certain functions, we will need a different tool, however. This will be given in the next lesson about implicit differentiation.